So in the last video, we started the derivation for how to get the general current density in a diode of any length, or so for any length p-n junction diode. And we came up with our boundary conditions gave us two equations. A plus B equals delta np naught, and A times e to the minus w over ln plus b e to the minus w over, or e to the plus w over ln is equal to 0. And so these two equations, we need to figure out from this the electron concentration delta n as a function of x, and from this we can get the current density J as a function of x, or J really just J throughout the semiconductor, because J has to be the same if we're assuming that we're not storing any charge. Okay, so we've got a set of two equations and two unknowns, so we're just going to use linear algebra to solve these. So our two linear equations involve A and B. So if we just set up our matrix, we get 1, 1, and delta np naught. We get e to the minus w over ln, e to the plus w over ln, and 0. And so if we just do some simple row reduction, if we subtract the first row from the second row, multiplying everything by e to the minus w over ln. So first row times e to the minus w over ln, subtract that from the second row, we'll get 1, 1, and delta np naught, just like we had before on the top. And here we'll get a 0, e to the w over ln minus e to the minus w over ln, and I should probably scoot over this delta np naught here. Let's just erase that real quick. Delta np naught, and then minus e to the minus w over ln times delta np naught. Okay, so we're just going to make a really quick simplification. We know that e to the w over ln minus e to the minus w over ln. First, that's a mouthful. But second, it's equal to 2 times sinh of w over ln. And that just makes our life a little bit easier. So we're just going to make that substitution here. And if you haven't seen that before, sinh is in the family of hyperbolic functions. This is sometimes considered its definition, but it's very useful in math and just in general in simplifying things. So 2 times sinh of w over ln. And so now we can further simplify this. I'm going to multiply the whole bottom row by 1 over 2 sinh w over ln, just so that we can get a 1 out front, and we know what our b is equal to. And it'll allow us to simplify things more easily. So we get 1, 1, 0, 1, and then we've still got delta np naught on the top. On the bottom, we've got negative delta np naught times e to the minus w over ln divided by 2 sinh w over ln. This is starting to get a little ugly, but not terrible. And so now we're going to subtract the second row from the first row, and we're going to get our final set of our final matrix, which will give us our solution. So this is 1, 0, 0, 1. And this is still the same, so delta np naught e to the minus w over ln divided by 2 sinh w over ln. And then on top we have delta np naught minus a negative, so that's plus, plus delta np naught e to the minus w over ln over 2 sinh w over ln. And so we can simplify this a little bit further by multiplying this np naught, or by multiplying out this np naught. First, let's just write out our answer. From this, we got that A is equal to delta np naught times 1 plus e to the minus w over ln over 2 times sinh of w over ln. And I should close off the parentheses. And we got b is equal to delta np naught. Wow, that looks like a p. Delta np naught times e to the minus w over ln over 2 sinh w over ln. And if this seems a little algebraic and nasty, it's because it is. I apologize. That's sort of just the nature of simplifying this. One of the reasons I'm doing this explicitly is because it's not actually gone over in the textbook, and I was never able to figure it out as an undergraduate. Neither could my professor. So I'm just going over this here so that we can have it for reference. And so we can simplify this top equation by multiplying the 1 by 2 sinh over 2 sinh, which is just e to the w over ln minus e to the minus w over ln. So a is just equal to delta np naught. So this is our old 1, and this is plus e to the minus w over ln, all divided by still 2 sinh of w over ln. And I just ninja'd in that 2 sinh of w over ln is equal to e to the w over ln minus e to the minus w over ln. Okay, so here we can immediately see that these two terms cancel, and we're left with something that looks a lot like our answer for B, and that's that A is equal to delta np naught times e to the w over ln over 2 sinh w over ln. And so A and B look really similar, except B has a minus w over ln up top, and A has a plus w over ln up top. Also, I just realized that B should actually have a negative out front. I'm not sure where I dropped that. Oh, yeah, I just forgot to write it in. It does have a negative in the matrix form. Okay, so now we can plug these back into our original equation, that delta n as a function of x is equal to a e to the minus x over ln plus b e to the x over ln, just using a and b. So that's a is just equal to, and I'm going to pull out the delta np naught over 2 sinh w over ln. I'm going to pull that out from everything because that's a common factor between everything. And we're left with e to the w over ln times e to the minus x over ln plus e to the minus w over ln e to the x over ln. And in my opinion, this is probably the most difficult part of semiconductor physics or any engineering discipline in general. It's keeping very precise track over all the terms, making sure you don't miss a negative sign here. And see, we already missed a negative sign, so B should have been negative. So this plus term, this plus becomes a minus. So even I'm doing it right now. So it is the most challenging part for a lot of people, I think. And we can simplify this a little further if we group these terms. So if we're just focusing on what's inside the brackets, we get e to the w minus x over ln minus e to the minus w minus x over ln. And this is just, we know, 2 times sinh of w minus x over ln. And so our final, this is just what was inside the brackets. And so if we want to write out our final carrier concentration as a function of x, delta n of x, that's just delta np naught times 2 sinh w minus x over ln divided by 2 sinh w over ln. And the 2's here cancel, and we're left with this final expression. Or if we expand delta np naught, we'll get that our final carrier concentration, delta n as a function of x, is equal to nn naught or let's actually just say NP naught times e to the Vd over phi t, the diode voltage, minus 1, times this term that we just calculated, sinh of W minus x over ln over sinh of W over ln. And we know that NP naught is just equal to NN naught times e to the minus VBI over the thermal voltage phi t. So this is our final expression. And this is general. This works for any diode of any length. And it's actually reasonably simple because it looks like our old equation, just this term, but it's got this sort of nasty multiplication factor at the end. Now, if we want to calculate the current instead of just the hole or the electron concentration, we'll get that Jn should just be Q times Dn times the derivative with respect to x of this whole thing. So we get a -1 out front, and differentiating this sinh of W minus x over ln, it's very similar to differentiating sine. You just get a ln, 1 over ln out front, and it becomes a cosh. So all this times NP naught times e to the Vd over phi t minus 1 times this term, sinh of, or no, sorry, this is cosh. And if the trig expressions are making you uncomfortable, just know that they're only really there to wrap the exponentials. So cosh of W minus x over ln. They're supposed to make things look less confusing. They don't always do it successfully. Sinh of W over ln. And so we're almost done. And if we want to find the current, we know we can plug in any value of x we want, so long as we evaluate Jn and Jp at the same, essentially the same x. And so x equals 0, we said, was the best way of doing that. So if we plug in x equals 0, and say we're only interested in Jn set. So we're not interested in this e to the Vd over phi t minus 1 term, because we know that's going to pop out the end. That's going to be multiplied by whatever answer we get. So we'll get that Jn set is equal to minus q times dn times, or sorry, there should be a plus q because the charge is negative. So we get a negative out front from the differentiation, but then another negative from the charge. So my mistake, positive q times dn times np naught over ln. And this was our old reverse saturation current density. This was what we derived for an infinitely long diode, except now it's multiplied by cosh of W over ln over sinh of W over ln. And if we want to make things even simpler, or at least from a writing perspective, this is equal to Jn sat ideal, or our ideal saturation current density from an infinitely long diode, times coth W over ln, which is 1 over cotangent of W over ln, which is just a way of writing 4 exponentials in the smallest way possible. Now, the interesting thing about coth is that it falls very quickly to 1. So for if W over ln is, say, equal to 2, coth of W over ln in that case, which is just coth of 2, is equal to 1.03. So as long as W over ln is greater than 2, or W is greater than 2 times ln, our ideal current saturation density was within 3% of the actual current reverse saturation current density. And so that's kind of awesome, because that means we don't really need to worry about this nasty expression so long as we have a reasonably long diode, so long as it's longer than the diffusion length. Another interesting observation is that this term is always greater than 1. So in other words, the current that we predicted, the ideal current from our diode, is actually an underestimate, or it's always going to be an underestimate. It might be a slight underestimate or a large underestimate, but that's always going to be, our ideal expression is less than the reality. So thank you all for watching. I realized that this was a bit of a slog through algebra. I just wanted to put it up on the web so that people have a complete reference for how to get this expression, since I had so much difficulty with it when I was an undergraduate. So again, thank you all for watching. If you have any questions or comments, feel free to post them down below, and I'll see you next time. I just